So in order to arrive at our differential amplifier, we're going to look a little bit at some very common circuits that we see in the lab, that we saw on the earlier, on the level 1, and hopefully in classes somewhere. So we have our non-inverting amplifier. Looks like that. And then you could draw another one, an inverting amplifier. So everyone probably knows these by now. So if we're trying to get a difference of something, and we know that the output of this is going to be some positive gain, and this is going to be some negative gain. And we know that with superposition, because these are linear circuits, if we could somehow combine the circuits, where we get a positive gain coming out of this amplifier and negative gain coming out of this amplifier, then we could measure a difference, or we could amplify a difference. So if you look really closely at these two circuits, it's really the same circuit. So in the non-inverting case, we put the V in on the non-inverting terminal. This side's connected to ground. In the inverting case, the V in goes into this resistor R1, and then the non-inverting input is connected to ground. But it's really the same circuit. Like you could see, if I just switch these around, literally, if this goes to ground, and that's the V in, it's the same as this circuit, it's just drawn a little differently. So we could take advantage of this in order to make a differential amplifier. Like literally, we could drive both inputs simultaneously. Call this one V in positive and V in negative over here. So now we're going to quickly analyze the circuit. So we have a non-inverter combined with an inverter, and we know we could use superposition to combine the output responses of both of those because it's a linear circuit. That's assuming that we don't saturate anything. And we have V in positive. This is the non-inverting gain amplifier. And I'm going to write the equation a little differently. It's going to be R1 plus R2 divided by R1. Most of the time you see it as 1 plus R2 divided by R1. But this will make our math a little easier. Equals V out. Then the non-inverting amplifier gain equation is going to be minus R2 over R1 equals V out. So we could combine both of those. So you have V in positive R1 plus R2 divided by R1. And then here we'll just put this minus sign out here. Minus V in negative R2 over R1 equals V out. So with the differential amplifier, what we're trying to do is only amplify the difference. And you can see right here, our equation's saying that we could do that. So it turns out that if this weight right here equals this weight right here, right? In other words, if these constants were the same, then we can make an equation that would look like this, where you'd have some K times V in positive minus V in negative equals V out. And that's really the response we want to get right here. So what we could do is we could figure out a way to make these two constants right here equal. And an easy way to do that, it turns out, is if we put a constant or some kind of amplification on the non-inverting input, which is easier because no current flows into it. If we tried to do it with this one, it gets complicated. So we're going to have a block right here called C, right? And that could be a gain of, greater than or less than 1. And then what we could do is, because it's in series, it's going to get multiplied by this part right here. So if we have R1 plus R2 over R1 times that C constant, and we set that equal to this gain equation right here, 2 over R1. And that looks like it's pretty easy to solve for C. Let's move the board up a little bit. Oops, something to fall off the table. So we could just cancel those two out, and C is just going to literally equal R2 divided by R1 plus R2. Now this might look familiar right here, this equation. And actually, it is familiar. It's the voltage divider ratio equation. You've probably seen this a bunch of times where you have a source, you have an R1 and an R2, you have a VN, V out, and then the voltage divider equation is just Vn times R2 divided by R1 plus R2 equals V out. So there it is right there. Right, that's the same as this equation. So we could take our voltage divider and put it in for C. Literally just take that out, draw on the voltage divider network. That's R1. Don't have a lot of room right there. And that's R2 connected to ground. And now we have a differential amplifier. So now we could clean up the math a little bit right here. So we solved for, we put a constant in this equation, right? We put the C in there in order to make this whole weight equal to that weight. So that's what adding this voltage divider here did. And because we set this equal to this, we kind of specified that R2 over R1 is going to be the K right here. So now it turns out that the gain of our differential amplifier, really works out nice and simple. It's just R1 over R2 and Vn positive minus Vn negative. That equals V out. And if you think back to the Wheatstone bridge, the nice thing about this is that we're only amplifying the difference between these two by this R2 divided by R1 coefficient. Like, in other words, when we were thinking about our Wheatstone bridge, which I dropped on the ground. Okay, here's our Wheatstone bridge again right here. So if Vn positive is over here and Vn negative is over there, if both of these change simultaneously from, say, something like the V positive getting larger, right there, V positive, in other words, the power supply got larger, and these both ratiometrically went up the same, then because it's getting amplified by this equation right here, if these change by the same, there's not going to be any contribution to V out. And that's really the beauty of the differential amplifier. The only thing that we could really measure is the difference between these two terminals. And from this circuit's point of view, the only way this is going to change is if the resistor in question changes.